Hello, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning. And the topic which we are covering is Monte Carlo and temporal difference methods. This is topic number 12 in the list of topics covered in this course. The subtopic is B. So the lecture is 12B. So the difficulty is from easy to moderate. And this video is based upon the supplemental material available at www.easymcq.com/GoGet, which is a personalized learning management system. So, what is the future of content delivery? That is not the future alone, that is also the present, because there are literally hundreds and millions of end users who are getting educated using the content delivery platform and mechanism, which are in hundreds and millions. So, that is the approach which is being used in delivering and explaining the concepts in this course. So, the personalized learning management system is accessible using the URL which is given in green color, and the content delivery mechanism is explained using 6 videos, and those videos are accessible using the link given in blue color. So, what are those features which I've mentioned? These features consist of advanced and basic content search, which is not there in leading learning management systems. And then, of course, the ability to support people with visual disability, such as changing the font size, color, line spacing, and so on. And then this content is organized in such a way that it can efficiently use the limited speed, the limited space and the speed of a handheld device. And of course, you can track your progress, what you have seen, done, and what you need to do. And then, of course, you also can test yourself online in real time, your knowledge assimilation and knowledge capturing. So, how the content is delivered? The content delivery can be question and answer based, and it can be traditional slides based. Now, the question and answer based approach is engaging, is proactive, it promotes thinking, and of course, it is very productive also. And the traditional approach contains a lot of details. So, the approach we have been following in this course is a blended approach, which is the best of both. So, this is the list of topics which are covered in this course, and we are at topic number 12, and this topic is further divided in. So here is the breakdown of the 2 videos for Monte Carlo and temporal difference methods. So the easy type of concepts are covered in shown with the yellow background, which is lecture 12A, and from easy to moderately difficult concepts are covered in lecture 12B with the green background. So now we are at 12B video for deep reinforcement learning, Monte Carlo and temporal difference methods. So, how do Monte Carlo and temporal difference methods handle the trade off between exploration and exploitation? That is kind of tricky. How that trade off is handled. So, we have that agent here, and the agent can either do exploration or exploitation. So, in exploration, select random action, and exploitation, select the best known action. So these are the choices. So, we have that epsilon greedy approach in reinforcement learning. So what happens is that the agent usually selects an action based on its reward, and the agent always chooses the optimal action to generate the maximum possible reward. Now this is basically a greedy approach. So in epsilon greedy action selection, the agent uses both exploitation to gain insights from the prior knowledge and exploration to look for new options. So it's a combination. So the epsilon approach or the method usually chooses the action with the highest expected reward. Their expectations. Now the goal of this approach is to achieve a balance between exploration and exploitation. Now with a small probability of epsilon, the option is to explore instead of exploiting what the agent has learned so far. Now, note that Monte Carlo and temporal difference methods both uh, go through this exploration and exploitation trade off, but the approach is different. For example, Monte Carlo emphasizes exploration using the full episodic returns and the knowledge and the stochastic policies uh, so as to ensure diversity in experience gathering. The Monte Carlo approach updates slowly but thoroughly, while on the other hand, temporal difference prioritizes speed and responsiveness. It updates incrementally using the bootstrap values. So, what do these values contribute? Basically, they encourage faster convergence. However, the risk is under exploration. So, the choice of policy behavior and the nature of feedback and the adaptation speed, they all significantly affect how these methods manage the trade off. Ultimately, the ultimate winner or the beneficiary is the deep reinforcement learning, which benefits from these hybrid approaches that blend the broad exploration of Monte Carlo with the efficient learning of temporal difference. So that ensures a balance between discovery and reward maximization. So let's look at this in more detail. So, with reference to the policy behavior, Monte Carlo methods often use the stochastic policies and they maintain exploration to collect diverse trajectories. Now, the advantage of this approach is that avoids premature convergence. Now, on the other hand, temporal difference methods usually and typically rely on epsilon greedy policies. So they kind of lean towards the exploitation, unless, of course, exploration is explicitly encouraged. Now, temporal difference bootstrapped updates tend to drive the policy towards greediness faster. So greediness kind of takes over quickly. Now, therefore, makes so we have to make careful exploration management so as to avoid getting stuck into local minima and to avoid suboptimal learning outcomes. All right. So then is the learning feedback. What is learning feedback? Monte Carlo methods use, as we have discussing, episodic returns that offer complete but delayed learning signals. Now, what it does is that this encourages continued exploration and provides unbiased estimates. Now, temporal different methods use what is called as the stepwise feedback, which is faster and is more data efficient as compared to temporal difference, but potentially biased if there is less exploration or if the exploration is lacking. Now, this difference in the feedback obviously directly affects how each method adjusts its policy. Adjustment in response to new experiences and how to manage the exploration exploitation balance. So now we move to adaptation speed. So adaptation speed basically temporal difference learning adapts immediately after each action. So this is very quick to learn and therefore it can support fast policy updates and online learning. However, obviously, this speed makes it effective in, of course, dynamic and changing environments like self-driven cars under traffic conditions in a busy street. But they are prone to instability if they are not properly balanced. So, on the other hand, Monte Carlo methods, although they are slower to adapt due to the episodic updates, but they are more robust in for long term basis. So the difference reflects a trade off between the reactivity and the stability in learning. Reactivity and stability in learning. So this is more of this stability than the this exploitation and exploration trade-off. So let's move on. So there's something new here now. On policy and off. What is difference between on policy and off policy learning? In the of course in the context of Monte Carlo and temporal difference learning methods. So this is the logical diagram here. So I will explain all of this. So now the thing is that exploration and exploitation trade-off is fundamental in deep reinforcement learning. Okay. However, the on policy versus off policy distinction, like that determines how agents actually manage that trade-off. Now, policy behavior, which we covered in reinforcement learning, that determines whether exploration and learning align or they diverge. Now, like learning feedback illustrates how updates incorporate the sample returns or the bootstrap estimates and the correctness for policy mismatch are needed. Now, then, of course, is the adaptation speed. That shows the adaptation speed shows how rapidly methods incorporate new experience, as we have discussed. So, in Monte Carlo and temporal difference methods, uh, on policy methods enforce consistency on policy, but they limit flexibility and rate of change. Whereas for off policy methods, they allow more aggressive learning and separation between exploration and exploitation. But there's a cost to it, and that cost is the increase in complexity, the increase in variance, and the challenges of stability. Now, together, these they all govern how effectively agents can explore, learn, and adapt in complex environments. Now, before we move ahead, let me explain these figures to you. Now, in the figure at the top, which is on policy, deep reinforcement learning, we can see that the policy, okay, which is represented by pi, is updated by streaming data, which is collected by the policy itself. Now, in the classic off policy setting, which is shown in the diagram below, the agent's experience is appended to a replay buffer D, replay buffer D, and each new policy represented by pi collects the additional data such that this buffer D is composed or consists of samples from say pi 1, pi 2, and so on. And all of this data which is in the buffer is used to train and update the new policy. So what do we get from here? Uh, what we get that this this is showing us that the off policy algorithm evaluate and improve a policy which can be different from the policy that is used for action selection. Okay. Now, what has been demonstrated over the period of time is that most of the on policy and off policy deep reinforcement learning algorithms successfully were able to be applied to the field of simulated games. But these currently cannot be directly used and operated in the real world physical environment. The reason being that both techniques require active online data collection and where the controller has to actively interact with its environment. Now, so what's the problem? So these are good methods, but the problem is that they are difficult to scale up for complex real world problems. Why? Because there are large data sets of active data. Okay, so that active data collection is impossible and it can be potentially unsafe also. So let's go into more details. So starting with the policy behavior. So that policy behavior basically distinguishes whether the behavior policy for example, used to collect the experience, is same as the target policy, which is used for learning. So now what happens is that in on policy methods, these two are identical. Collection and learning are identical. So that kind of constrains the exploration to occur under the same policy. The agent seeks to improve. Now, on the other hand, off policy methods decouple instead of coupling them. So decouple them. So of course that allows more exploratory behavior while learning a more optimal target policy. So this flexibility gives off policy methods greater power, but they require correction mechanisms. For example, importance of sampling or careful bootstrapping to account for the mismatch. So this is kind of tricky. So learning the feedback. Now it's not learning the feedback, it's the actually the correct word is like learning feedback. So learning feedback refers to how value or policy updates are computed using the already observed data. Now, now only the on policy of Monte Carlo methods uses full returns directly, but the off policy of Monte Carlo applies importance sampling to correct for policy mismatch. Now, for on policy temporal difference, updates via bootstrapping uh, for the next state estimates under the same policy. But the off policy temporal difference, like secure learning, that updates using the greedy target policy and estimates regardless of whatever is the behavior of the action. So now we see that there are differences in the feedback. So these feedback differences affect the bias, they affect the variance, and they also affect the stability of the convergence. And this overall dictates how elaborately we must manage exploration and exploitation. That is the key. So it is not simply a greedy approach or epsilon approach which is going to help us, but it requires more work. Then is the adaptation speed. Now this speed, as a matter of fact, addresses how quickly a reinforcement learning method responds to new experiences or the environmental shifts. So that, as a matter of fact, dictates the application domain also. Now off policy methods can adapt faster by how? By separating behavior and the target policies. And as a consequence, this allows more aggressive learning without the without disrupting exploration. Now, on the other hand, the temporal difference methods, due to their incremental or step-by-step approach, adapt faster per interaction as compared to Monte Carlo. Why? Because Monte Carlo has to or must wait until the episode's finished. Yet, the faster adaptation increases the risk of instability, increases the risk of divergence, and therefore it requires some additional mechanisms to control this and to maintain stability in learning. And of course, that adds processing time, that adds the cost also. So, again, there is a trade off. So, quite a few trade offs are required to be made. All right, so we move on to the next Q&A, which is what are the limitations of Monte Carlo and time difference methods in reinforcement learning? So, what are these limitations of these two techniques? Well, what we have gathered up till now is that the exploration and exploitation trade off is critical challenge in deep reinforcement learning. So, there has to be a balancing and a need to discover new strategies versus exploiting the known but the good ones. Now, these two methods, Monte Carlo and temporal difference, offer complementary approaches to value estimation, but both of them have distinct limitations. Now, for example, Monte Carlo methods provide unbiased estimates, but they suffer from higher variance and they suffer from slow updates. And then, of course, they rely on complete episodes, which basically restricts their application in changing dynamic or complex environments. On the other hand, temporal difference methods although offer faster and incremental learning, but they introduce bias and that quick learning has the stability risks, especially when there has to be function approximation. So, in a nutshell, both methods require thoughtful handling of exploration to ensure learning effectiveness. So, again, we are back to the exploration and exploration trade off. Understanding these trade offs helps practitioners design algorithms suited to their environmental demands, and that often motivates hybrid approaches. So, which is trying to leveraging the strength of both Monte Carlo and the temporal difference methods. Now, in this, here are some more details which we will cover. All right. So, the approach we will this concept is more focused towards Monte Carlo methods, and we'll be using something of which is called as the Monte Carlo tree search (MCTS). So, what is that Monte Carlo MCTS? Basically, this is an approach which consists of, as you can see, four phases. Selection, and you can read them. I don't have to read it for you. So what happens in the selection phase that it starts from the root node and there is a traversal down the tree. So starts from the root node and traversal down the tree using a certain selection policy. And there are different approaches, there are different formulas, and these kind of balance between exploration and exploitation. And how they do that using the formulas, and they select the child nodes with this is selected, or this is selected, this is based upon their average reward and uncertainty. So that's the selection. That's one step. Then is the expansion phase. This is the expansion phase. So now when this selection phase reaches a leaf node, which is not the terminal, all right. So the algorithm has to further expand by, say, for example, adding one child or more children, say to say, okay. And why we are doing that? To looking for possible actions from that state. So one step ahead. We stopped here, and expansion went further. Then is the simulation phase. Now we have added this node. This is the new node added. This is new node added. All right. Now a random kind of a scenario is kind of generated or performed to reach a terminal state. So this will reach a terminal state. Now, now in this simulation, okay, random moves are chosen using simple heuristics. Why? So that the simulation is computationally inexpensive. It's not very expensive. And then finally is the back propagation. Now this result of these simulations, all right. So we this is the selection of a child, then you expand, then you simulate, and then propagate back up to the root of the tree. And on this way back, keep on updating the statistics such as visit counts and win rates and so on. And this is done for all nodes visited during this route, okay, for the selection phase. Now we will also look at the limitations of this approach also, okay, this approach. So this Q&A is more about Monte Carlo methods than about the temporal difference methods. So let's look at, before I actually move, I should open this. So we look at the exploration exploitation trade-off. All right. So what is this? So in this trade-off, it is a balancing act, discovering new information, which is exploration, and using known rewarding actions, which is exploitation, making the most of what is already known. Now, in deep reinforcement learning, managing or making this trade-off or this balance is complicated. When it becomes complicated, because when there are large state spaces and when there are delayed rewards. Now, if this management is poor, okay, there is a risk of premature convergence or slow learning. Now, we discussed the strategies like those epsilon greedy or like intrinsic approaches. They may help, and they can be used to maintain effective exploration without sacrificing exploitation, which of course is critical for learning efficient and robust policies. The limitations of Monte Carlo we are going to discuss in more detail. Temporal difference limitations. Now, these methods, although update incrementally using those bootstrapped estimates, which enables fast learning, but it introduces bias. Now, this bias can cause instability or it can cause divergence, and this is more profound with function approximation or if the parameter tuning is not proper or poor. Now, remember that temporal difference, or if you don't remember, temporal difference is sensitive to noise and it is prone to overfitting. That's a limitation. Overfitting for recent experiences, and they require certain techniques for stability. So, but still, temporal difference is crucial for scalability despite those challenges. Now, more specifically, the limitations of the Monte Carlo technique and the edge cases. All right, Monte Carlo techniques and the edge cases. So, not going a lot of details about temporal difference. So, so major limitation of Monte Carlo system is it requires a lot of simulations, and these simulations are done and required for reliable estimates, and obviously for complex domains. Now, this can be computationally expensive, requiring a lot of CPU cycles, requiring a lot of energy also, and that becomes a bottleneck when quick decisions are needed. So that's an issue. Then is the high variance of the uh, Monte Carlo techniques, because if the simulations are done randomly, random simulations, okay, so that can produce inconsistent results, or they can have inconsistent results, especially in games. So there where the variance can be very high. So you need to use additional techniques to mitigate these issues, and these additional techniques again contribute more processing power. Now, specifically for MCTS, which we just discussed and I showed you, that can miss short-term good opportunities. Why? Because of its reliance on randomness. For example, if playing chess, the algorithm might overlook a forced checkmate sequence. Why? Because it may have, or because the simulation could fail to, or fail in finding or performing the variations in exploration. And finally, we come back again to the same problem: exploration exploitation balance. Because the formulas which are used in Monte Carlo tree, okay, requires careful tunings of what exploration constant. Now, if this balance is lost and there's too much exploration, that results in inefficient search and loss of CPU cycles also. Now, if it is on the other extreme, it is too little, so that can result the algorithm to get stuck at the local optima, and then of course optimization is hard to achieve. So we see that this is again a challenging task. Okay, so if you're interested, here are the details of what I have just discussed. Okay, and here are the references for about what I've discussed and for further reading if you're interested.